Welcome to the deep dive.
Hello.
Today, we're jumping into artificial intelligence, specifically how these systems actually learn.
Right. It's kind of the magic behind things like, your phone recognizing your face.
Exactly. Or how streaming services just know what movie you want next. It's all about this learning process.
Yeah, and that's what we want to unpack in this deep dive. Give you a clear, sort of accessible way to understand AI learning, focusing on machine learning.
Without getting totally lost in the tech speak.
Well, hopefully. We're working from an explanatory report here, breaks down the main ideas, and we'll be using this analogy throughout.
Ah, the toddler and the cats.
That's the one. Teaching a toddler to spot cats, it helps make the complex bits feel a bit more grounded.
Okay, sounds good. So let's kick things off then. Big picture first. What actually is artificial intelligence?
Well, at its heart, AI means computer systems that can, mimic cognitive stuff humans do.
Cognitive stuff.
Yeah. Like understanding what's in a picture, recognizing speech, making decisions, translating languages, those sorts of tasks.
And a key thing about AI, it's not just a fixed program, right? It gets better.
Precisely. That's the learning part. Unlike, say, your calculator that just does what it's told, AI systems can actually learn from the data they see.
They adapt.
Yeah, they adapt, improve their performance. They're not static.
Yeah. Broad strokes understood. Now let's zoom in a bit. Machine learning. We hear that term all the time. How does ML fit in?
Right. So machine learning, or ML, is a specific way to AI. It's a subset.
A subset meaning?
Meaning instead of a programmer writing out every single instruction step by step for the computer.
Like traditional coding.
Exactly. With ML, the computer learns from data. We give it examples, and it figures out the patterns itself.
Ah, okay. So back to the cats. Instead of describing pointy ears, whiskers, fur, you just show it loads of cat pictures.
You got it. You show it thousands, maybe millions of pictures, some cats, some not cats, and the machine learning algorithm learns to tell the difference by finding the common features in the cat examples.
So it's pattern recognition, basically.
Yeah.
Drawing conclusions from the examples.
That's a great way to put it. It identifies patterns in the data it's trained on and then uses those patterns to make predictions or decisions about new data it hasn't seen before.
Kind of like how we learn, right? Practice makes perfect, or at least better.
Yeah, there's definitely an analogy there. Improvement through experience, or in AI's case, through data.
Okay. That clarifies ML. But then there's deep learning. Sounds deeper. What's the deal there?
Yeah. Deep learning, or DL, is actually a subfield within machine learning, so it's even more specific.
Okay.
It uses particular kinds of structures, very complex ones, called neural networks.
Neural networks. Inspired by the brain, I hear.
Loosely, yes. Very loosely inspired by the network of neurons in our brains. They have these interconnected layers that process information.
And the deep part just means lots of these layers.
Pretty much. Lots and lots of layers, could be dozens, hundreds, even thousands. And having all those layers allows DL models to learn really, really complex, intricate, abstract patterns from huge amounts of data.
Which is why it's used for the really cutting-edge stuff.
Exactly. Things like really accurate image recognition, understanding human language. That's often deep learning at work.
Okay, so maybe that analogy you mentioned earlier could help place these AI, ML, DL.
Yeah, the Russian nesting dolls.
Yeah.
Okay, so imagine the biggest doll. That's AI, the whole big idea of intelligent machines.
Got it.
Then you open it, and inside is the next doll, machine learning. That's a specific way to achieve AI, the learning from data approach.
Okay.
And then inside the ML doll is the smallest one, deep learning. That's a specialized type of ML that uses those deep neural networks we just talked about.
AI contains ML contains DL. Okay, that clicks. Great analogy.
Glad it helps.
So now we know the what. Let's get into the how. How does this learning actually happen? What are the ingredients?
Yeah, the core components. There are really three main building blocks you need to understand. Training data, algorithms, and then, especially for deep learning, those neural networks.
Let's take them one by one. Training data. Sounds important.
It's fundamental, absolutely critical. Training data is the raw material, the knowledge base the AI learns from.
The textbooks for the AI student.
Exactly. Or the notes, the examples, everything the student studies. For AI, it's the data it analyzes to find those patterns.
So for our toddler learning about cats, the training data is...
It's all the pictures of cats we show the toddler, maybe real cats they see. Crucially, it's also pictures of things that aren't cats, dogs, chairs, cars.
Right, so it learns to tell the difference.
Precisely. And often this data comes in pairs. You have the input, the image, and the correct label, the word cat or not cat. The AI's job is to figure out the connection. How do these pixels relate to that label?
And I guess the amount and quality of that data really matters.
Hugely. You need lots of data, and it needs to be good quality, diverse data. If you only show the AI pictures of ginger cats,
It might not recognize a black cat.
exactly, it won't generalize well to things it hasn't seen in training. Just like a student who only studies one type of math problem might bomb the test if it looks different. Bias in data is a huge issue.
You mentioned different kinds of data.
Broadly, yes. Two main types. There's labeled data, like our cat pictures with the cat or not cat label. That's used for something called supervised learning.
Okay.
Then there's unlabeled data. That's just dot data, raw information, no predefined answers or categories. That's used for unsupervised learning, where the AI has to find patterns on its own.
Interesting. Okay, so data is the fuel.
Right.
How does the AI actually use it? That's the algorithms, right?
Correct. Algorithms are the recipes, the sets of rules or instructions that tell the AI how to learn from that data.
The students' learning strategies,
Hmm.
like memorization versus problem solving.
That's a good analogy, yeah. Different algorithms are like different strategies for learning.
And I bet there's more than one type.
Oh, many. But they generally fall into three big categories, often based on the type of data they use and the goal. Supervised learning algorithms, unsupervised learning algorithms, and a third one called reinforcement learning algorithms.
Let's start with supervised learning. That uses the labeled data.
Yes, supervised learning algorithms learn by example. You give them inputs paired with the correct outputs. The goal is to learn a mapping, a relationship between the input and output.
Like the spam filter example.
Classic example. You train it on emails already marked spam or not spam. That's the labeled data. The algorithm studies the features of those emails, words, sender, etc., and learns the patterns associated with spam.
So then it can look at a new email and predict if it's spam or not.
Exactly. It's learned the mapping from email features to the spam not spam label.
What else uses supervised learning? Feels like a lot.
It is very common. Image recognition, like identifying cats and dogs, that's often supervised. Predicting house prices based on features like square footage, number of bedrooms, that's supervised too.
And specific algorithms for this.
Yeah, common ones include things like linear regression, if you're predicting a number like a price, logistic regression for yes-no type classifications like spam, and decision trees, which sort of make a sequence of branching decisions.
Okay. Now, unsupervised learning. That was with the unlabeled data, where there's no right answer given.
Right. With unsupervised learning, the algorithm is thrown into the data and basically told, find something interesting. It looks for hidden structures, patterns, or groupings within the data itself.
How would that be used?
Imagine you have tons of customer purchase data, but no predefined categories for your customers. An unsupervised algorithm could potentially discover natural segments or clusters of customers who behave similarly.
Ah, so finding groups you didn't even know existed.
Exactly. It's about discovering inherent structure. Other uses are things like anomaly detection, finding weird outliers like potentially fraudulent credit card transactions, or just simplifying complex data by grouping similar things.
Is there a main algorithm for that?
A very common one is called k-means clustering. It tries to partition the data into a specific number, k, of clusters, grouping points that are close to each other.
Interesting. Okay, third type, reinforcement learning. That sounded different.
It is quite different. Reinforcement learning, or RL, is about learning through trial and error. An AI agent interacts with an environment, takes actions, and gets feedback.
Feedback like rewards.
Or punishments.
Exactly. Positive feedback rewards for good actions, negative feedback penalties for bad ones. Think of training an AI to play a video game.
Okay.
It tries moving left, maybe it gets points reward. It tries jumping into a pit, it loses a life penalty. Over many, many trials, it learns a strategy, a policy, of which actions lead to the best outcomes, maximizing rewards.
So it learns by doing and seeing what happens.
Precisely. It's learning from experience in an environment. It's really powerful for things where the sequence of actions matters, like robotics teaching a robot to walk, or self-driving cars navigating traffic, or even optimizing things like energy grids. Fascinating. Okay, so we have the data, fuel, the algorithms, recipes. Now, neural networks, we touched on them with deep learning. Let's dive a bit deeper there. What makes them tick?
Right. Neural networks, they're a type of ML model particularly good for complex stuff, as we said, inspired by the brain's structure. You have these layers of interconnected processing units, often called artificial neurons.
And how are they laid out?
Typically, you have an input layer that just receives the raw data, like the pixels of an image,
Okay.
then one or more hidden layers. This is where the real magic happens, the processing, the feature extraction, the learning.
And finally.
An output layer, which gives you the final result, like the probability that the image is a cat or the predicted price of the house.
And the connections between these neurons, they're not all equal.
No,
Yeah.
absolutely not. Each connection has a weight associated with it, a numerical value. This weight determines how much influence the signal from one neuron has on the next one. Learning, in large part, is about adjusting these weights.
So stronger connections mean more influence.
Exactly. And then each neuron also has an activation function. Based on the weighted sum of all the signals coming into it, this function decides if the neuron fires or not, if it passes a signal onward.
Like a threshold. Needs enough input to get activated.
Sort of, yeah. It introduces nonlinearity, which is crucial for learning complex patterns. And again, deep neural networks just mean lots of those hidden layers, allowing them to learn hierarchies of features, like first layers find edges, next layers find shapes, later layers find objects.
Okay, wow. Lots of moving parts.
Mhm.
Let's bring it back to the cat analogy one more time. How do data, algorithm, and network features all play together there?
Okay, let's walk through it. Our training data is the huge pile of pictures, each labeled cat or not cat.
Got it.
The algorithm we use could be, say, a basic neural network designed for image classification.
Right.
The network looks at the images and starts identifying features, maybe patches of fur, the pointy shape of ears, the presence of whiskers, eye shapes.
Things that tend to appear in cat pictures.
Exactly. During the learning process, the network adjusts the weights on the connections. Features that are strongly predictive of cat, like whiskers, will get higher weights, connecting them through the layers towards the cat output. Features common in non-cats get lower weights, or weights leading to the not-cat output.
So it learns which features matter most.
Precisely. Then, when you show it a new, unlabeled picture, it analyzes it for those features, uses the learned weights to combine their influence, and makes a prediction. Based on the features and their weights, I am 85% confident this is a cat.
That really ties it together nicely. But you made this point earlier, this is still different from how our actual toddler learns, right?
Hugely different. It's a vital distinction. The analogy helps explain the mechanics, but a toddler's understanding is way richer, more intuitive.
How so?
Well, toddlers usually need far fewer examples. They generalize much better. See a few cats, they kind of get catness. That's because they bring tons of prior knowledge, context about the world, object permanence, maybe even empathy. Things AI just doesn't have.
So current AI is more about the statistics.
Primarily, yes. It's incredibly powerful statistical pattern recognition based only on the data it was trained on. It doesn't understand a cat in the human sense.
It lacks common sense, intuition.
Exactly. But that ability to find patterns in massive data sets is the core principle. That's what these algorithms are built to do.
And it's not just finding patterns once, it's refining them.
Absolutely. The learning process involves constantly adjusting those internal parameters, the weights in a neural network, for example, to get better and better at matching the patterns in the data. It's iterative.
How does it know how to adjust? How does it get better?
That involves optimization algorithms. A very common one is called gradient descent. You can think of it very simplistically like trying to find the bottom of a valley.
The valley representing error.
Exactly. The difference between the AI's prediction and the right answer. Gradient descent is a mathematical way to figure out which direction to tweak the parameters, the weights, to go downhill to reduce that error.
So it keeps adjusting step by step to minimize mistakes.
That's the essence of it. A continuous cycle of prediction, error calculation, and parameter adjustment, all aimed at making the model more accurate.
And all this, the massive data, the complex networks, the optimization, needs a lot of computing power, I assume.
Oh, absolutely. The recent AI boom is really fueled by two things: the explosion in available data and the massive increase in affordable computing power, especially GPUs. Training these big models takes enormous resources.
Right. Okay, this has been incredibly insightful. To kind of wrap things up, can you give us the quick summary, the core principles of AI learning?
Sure. So basically, AI learns via machine learning. This means identifying patterns in large amounts of training data using specific algorithms.
Like supervised, unsupervised, or reinforcement learning.
Right. Deep learning is a type of ML using those layered neural networks to find really complex patterns. The whole process relies on the training data, for example, as the algorithms for the learning rules, and optimization methods to automatically adjust the system's internal settings, its parameters, to get better at predicting or deciding.
And hopefully, thinking about teaching that toddler to spot cats helps make those ideas stick.
Yeah, I think it's a useful mental hook. It captures the idea of learning from examples, feedback, finding features, even if, as we stressed, AI learning and human learning are still very different beasts.
But the principles are becoming clearer.
Definitely. We understand the mechanics much better now.
So, thinking about how fast this field is moving,
hmm
what's a final thought for our listeners to chew on?
Well, given how quickly AI learning is evolving, just try to imagine what capabilities might emerge next, things we maybe can't even properly conceive of right now. It's worth keeping an eye on, maybe doing your own digging online. There's so much out there to explore.